Hello, my name is Benjamin Grandsitter, and today I'll be going over lab number 6, magnet molasses. So the purpose of this lab was to see how a falling bar magnet interacts with a conductive aluminum tube, and then to model that interaction computationally, and then to compare the model's prediction to the actual drop time. The models and fundamental physical principles we used were the magnet is modeled as a magnetic dipole, the tube is modeled as a stack of conducting rings, Faraday's law where the changing magnetic flux induces current, Lenz's law where induced current opposes the change causing it, and Newton's second law where the net force determines the magnet's motion. So what were the predicted results, or what's a little introduction to the results? The magnet should fall slower than free fall inside of the aluminum tube because as it's falling, the changing magnetic flux will induce current, which causes a magnetic force. The average falling time through the tube was 1.24 seconds, and the computational model's predicted time was 1.108 seconds. So the assumptions we used were basically just that the bar magnet behaves like an ideal magnetic dipole, and the aluminum tube has a behaves as a stack of conducting rings, and that those rings don't interact with each other. We also assumed air resistance was negligible, and the models were the magnet is a magnetic dipole, the tube is a stack of conducting rings, and for motion, Newton's second law. So the experiment itself, the system was the falling magnet, the tube, and the induced currents in the tube, and the surroundings was basically just everything else in the universe. The initial conditions were the magnet is released from rest, the tube is held vertically, the magnet is centered as closely as possible to the center of the tube, and in the computational model, it starts at the upper rim of the tube. Basically what we did was we measured the tube's dimensions and the mass of the magnet, and then we performed 5 drops and then averaged the time of each of those drops, where we got 1.24 seconds as the average. So these were the results. The tube length was 48 centimeters. We did 5 trials, and the average was 1.24 seconds. It fell noticeably slower than free fall, which was about 0.3 seconds. And there's the math for you. So the code for the code portion, basically we just used, or I started with the starter code, and then basically just built a model where I first put in the properties of the tube and magnet, and then used the starter code to use Faraday's law to determine the induced current on each ring, and then use that to find the total magnetic force opposing gravity, and then the net force was found so that I could update the magnet's velocity as it fell computationally. And then those are the main equations used, Biot-Savart's law, Faraday's law, etc. So the results of the code portion, we found the time to fall to be 1.108 seconds. And the graph is there on the right, which is basically linear, except for the first fractions of a second. And then we have the actual model showing the magnet at the bottom of the tube, as well as the results. Here's the code. There's a lot of code. It's going to be very hard to read, but it worked, so that's good. So interpreting the simulation, so the intensity of coloring on the tube shows the current, which color corresponds to clockwise current and which is counterclockwise, and how do we know? So the clockwise current is the positive, and that color is red, and the clockwise is blue. We know this because the starter code basically just has positive current defined as red and clockwise, and then counterclockwise is defined as blue. What happens to the dynamics of the system when you flip the magnet around? Basically, the magnetic force has not changed, but the current direction does change. How does the total time in the tube of your real-world system compare to the computational model? The difference was about 0.132 seconds. And to make the model more accurate, we could have done things like model the magnet as a finite bar magnet instead of a point dipole, or use the model a more accurate magnetic moment. And then what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Basically, the plot tells us that initially the gravity is larger than the magnetic force, but over time they come to basically equalize and the magnet approaches an almost constant speed. So how close were the results? As I said before, the difference is about 0.132 seconds, which is about a 10.6% difference. This difference is actually pretty encouraging because it means our computational model is likely reasonable. And then when you take into account the possible sources of error, which I'll describe next. So the possible sources of error were the magnet was modeled as an ideal magnetic dipole, which it probably is not, and the magnetic moment was probably off, as well as a couple other things. So for the what if and why questions, if the resistivity of the conductor were reduced to as low as possible or close to zero, how would that change the falling magnet's dynamics? Basically, the resistance would go to basically zero, which would mean that the current would be much larger and the magnetic force would be larger. If holes or slots were cut into the tube, how would that affect the current in your model? Basically, if slots were cut into the rings of the tube, the current would be disrupted, meaning the magnetic force would be lower. In conclusion, this lab showed that a falling magnet will move much slower when moving through an aluminum tube than through air, and this is because the changing magnetic flux caused by the magnet opposes the falling motion. Thank you.